Hello, sorry. Hello everyone. Welcome to the next connecting video of the control systems. So till now we saw the mathematical modeling of mechanical system, mechanical rotational system we saw, which we converted into electrical system. Okay, in a mathematical format. If you see the exactly the whatever the mathematical conversion is there, that conversion is based upon the differential equation. That means a d square x by f equal to ma, that equal to f equal to m into d square x by dt square. So in that way it will be there. That means that whatever the mathematical modeling entirely which was happened in the last few videos are based upon the mathematical modeling based upon the differential equation. But now what we are going to do is we are going to see with respective to the next another one, that is called it as a transfer function model of electrical system. That means we are doing with respect to the transfer function. Okay, so that the topics what are covering in this one is mathematical modeling of an electrical system using transfer functions, not with respect to the differential equations here completely a electrical system, not we are considering any mechanical system, not we are considering any mechanical rotational system. Okay, so here the thing is mathematical modeling series part 2, which represents to the electrical system. First part is two or three videos will be there, that will be related to the mechanical system. This one is related to the electrical system. Now we need to understand what is the necessity to go into the mathematical to understand the electrical system. That is, if you see the whatever our electrical modeling electrical systems are there, that will be considered with respect to under currently we are discussing all the elements, all the whatever the equipment will be, that will be considered as a resistance or inductance or capacitance. That is the primary elements whatever we call it as. So that elements we are calling as a RLC circuits, we will call it as. So represents the differential equations. That means what are these are converting into electrical system with respect to transfer function, differential equation which we can convert into the transfer functions. Okay, which analyze and control the same, the whatever the things which we discussed in the previous part. The same way we can analyze the equations, we can easily control the equipment, or we can easily control whatever the exactly where which we need to control. Okay, so now we are going to see a basic block diagram of a RLC system. Okay, if you see here the AC system. Okay, that is the AC voltage. Okay, so this is the AC voltage, whatever system AC voltage or AC supply is there. That AC supply, it is having a current of I of t equal to Im sin omega t, because whenever you are dealing with the AC systems, the sine component will be always will be there, and also this omega, which is representing the frequency. So whenever the say AC sine AC supply related things are there, the frequency is very much when you are writing any equations. Okay, and after that this RLC are resistance and inductance and capacitance. All these three are in series. And the voltage is what with respect to resistance is VR, the voltage with respect to inductance is VL, and voltage with respect to capacitor is the VC. These are the voltage, and the supply voltage what we already know is that is considered as the VC, sorry VS. So these are the mechanical voltages and the currents which are flowing in this total circuit. Now we are going entering into the definition, the same circuit, and now I am writing in the time domain analysis, because initially we need to consider, or we need to convert the total system, whatever the electrical parameters are there, that we need to convert into the time domain, because the whatever each and every parameter, the resistance is sometimes depend upon the time, and inductance always depend upon time, capacitor always depend upon time. So that's why we need to uh, convert the total this entire circuit into the time domain analysis. So first we need to write with respect to the resistance, so that we are writing here, that is resistor is with respect to the resistor, that is equal to IR. Okay, as we already know with respect to the Ohm's law. Okay, right. In the same way with respect to the Ohm's law, we are having another with respect to inductor, that is with respect to inductor V equal to L di by dt. As I already said, inductor always depend upon the time, but in resistance will not be depend upon time. Very less cases it will be depend upon that time. So it is always depend upon time. The next one is the capacitor, that is I equal to C dV by dt. Here also if you see, that is depend upon the time. So both is depend upon time. Because of these two, the total whatever the system, whatever the circuit is there, the circuit you need to convert into time domain first. After that only we need to consider, or we need to design the system into electrical parameter or mathematical model. So using Kirchhoff's laws and Laplace transform, we need to derive the transfer function of this complete electrical circuit that we will be discussed in the next video. But you need to understand, or we need to remember these three equations very carefully. And after that only, we, as these are in series, we need to add them, or if they are in parallel, we need to what multiply or divide. We need to, according to that one itself, the equation will be formulated. Okay, thank you.